Hello student, welcome again in my channel Learn Physics. I have already uploaded the one-shot videos of all chapters of mechanics, gravitation and thermodynamics. These one-shot videos will be extremely helpful for your class 11 exam, main, NEET and advanced. Now today I will be discussing the elasticity. My discussions are first of all definition of elasticity, different type of stress and strain, elastic modulus, young modulus, bulk modulus, modulus of rigidity, Poisson ratio, stress strain curve, and finally the strain potential energy or elastic potential energy, and different types of numerical of above topics will be discussed. So this video will be very interesting for you. Please like, share and comment on it. Now let's start. First of all, elasticity. When a balanced force acting on an elastic substance such as rubber cord, steel wire, copper, internal forces developed in it. These internal forces opposes the balanced force which causes deformation. So elasticity is the property to oppose the deforming force or restore the original shape of the body. Now stress. When a balanced force acting on a body, a reaction force produced in it. This reaction force helps the body to restore its original shape or opposes the deforming force. This reaction force per unit area of cross section is called stress. Look at this. Suppose this is a substance. Its area of cross section is capital A. A balanced force F and F acting on it. So reaction force produced within it according to Newton's third law of motion is also F. So stress is the reaction force produced per unit area of cross section. Its unit is Newton per meter square and dimension m, L-1, T-2 just as pressure. Okay, now a numerical. Suppose a force of 10 kg weight is applied on it. Area of cross section, this is the 1 millimeter square. What is the stress? Look at this. So stress become, force is the 10 kg weight, so this is the 10 into 9.8 Newton is the force. Now area of cross section, this is the 1 millimeter square. If it is converted into SI system, it should be 10 to the power minus 6 meter square. Therefore, this is the 9.8 into 10 to the power 7 Newton per meter square is the stress on this substance. Okay. Now there are three types of stress. Now longitudinal stress. If a balanced force F and F acting along the length of a wire, the stress produced is called longitudinal stress. Longitudinal stress are of two types. One, tensile stress and other compressive stress. If the balanced force increases the length of a wire, then stress produced is called tensile stress. If the balanced force decreases the length of a wire, then stress produced is called compressive stress. Okay? Now normal and tangential stress. Look at this. Suppose this is a sphere. If a normal balanced force acting on this, then stress produced in it, if this balanced force is F, then normal stress S is equal to F divided by area of cross section. Now tangential stress. Look at this. If tangential force acting on this surface is keeping lower end fixed, then stress produced in it is called tangential stress. Tangential stress, this is the Ft divided by area of cross section on this surface. Okay, now a numerical. Now this is a cylindrical rod. A balance force F and F acting on it. We have to calculate tangential stress and normal stress. And when the tangential stress becomes maximum. Now this is a cylindrical rod. Its area of cross section A. Look at this, the balance force F and F acting on this rod. We have to calculate tangential and normal stress on the area A dash, which makes an angle theta with the area of cross section A. Okay, this is the A. Now the force acting on it along this direction is F. So the force, the component of this force along this component, this is the F cos theta, and component along this force is the tangential force Ft, this is the F sin theta. Okay, now area of cross section of this surface A. So area of cross section of this surface, look at this, A by A dash, this is the cos theta, therefore A dash equal to A divided by cos theta. Okay, understood? Now normal stress, look at this, the normal stress Sn, this is the F cos theta divided by A dash, so this is the F cos theta divided by A by cos theta. So look at this, this is the F cos square theta by A. Okay, understood? Now tangential stress, look at this, the tangential stress St, this is the F sin theta divided by this area. So this is the F sin theta divided by A dash. So look at this, this is the F sin theta divided by A by cos theta. So look at this, this is the F by A sin theta cos theta. Okay, now this is the 2 and this also 2. Look at this, 2 sin theta cos theta is sin 2 theta. So F sin 2 theta divided by twice A is the tangential stress. Now for what angle the tangential stress becomes maximum? Look at this, the tangential stress becomes maximum if sin 2 theta is maximum. That is 2 theta equal to 90 degree. So theta equal to 45 degree. So at the angle of 45 degree, the tangential stress is maximum. Okay, next, now braking stress. The braking stress is the braking force divided by area of cross section. Now braking force F equals to, so this is the braking stress into area of cross section. Now after certain extension of a wire, the wire breaks. The force required for this braking is called braking force. Now braking force F equals to braking stress into area of cross section. So braking force is directly proportional to area of cross section. Greater the area of cross section, greater the braking force. Now A is the pi r square. So look at this. So here F proportionate r square. So double the radius of cross section of wire, 4 times is the braking force. Okay, double the area of cross section, double the braking force. It also depends on material but independent of length of a wire. Okay, that is braking force for a wire of length L and 2L are identical. This braking stress, which is braking force by area of cross section, depends only on material. Okay, now a numerical. Look at this, a wire of diameter 1 centimeter break, if force applied on it is 500 Newton. Now what is the braking force of same wire having diameter 2 centimeter. Now look at this. We know the braking force is directly proportional to square of the diameter of the cross section. So look at this, here F proportionate D square. Okay, therefore F2 by F1, this is the D2 by D1, this is the square. Okay, now this is the 1 centimeter, this is the 2 centimeter. So this is the 2 by 1 whole square, and F2 whole divided by, this is the F1, this is the 500. Therefore F2 equal to 500 into 4, that is 2000 Newton is the braking force for this wire. Okay, next look at this. The braking force for this wire is 40 kg. Now it is cut into two equal parts. What will be the braking force of this? Look at this, this is the length L and this is the length twice L. We know the braking force is independent of length of it. So it does not depend on length of the wire. It depends on material and area of cross section. Look at this, the area of cross section, this and this same. And this is the same material. So here braking force, this is the 40 kg watt also. Okay. Understood? Strain. Strain is the ratio between change of dimension by original dimension. Like stress, strain are also three types. Longitudinal strain. Look at this, longitudinal strain. Now longitudinal strain is the change of length by original length. So look at this, this is the change of length small length by original length capital L. Okay. Now volume strain. Volume strain is the change of volume divided by original volume. And shearing strain. Now shearing strain. Shearing strain is the shift of the surface divided by edge of the surface. Look at this, if a tangential force acting on the surface keeping lower and fixed. Look at this moves by x. So look at this is the x. Look at this is the x. Okay. So look at this, the shearing stress is the displacement of top surface keeping lower surface fixed divided by edge of the surface. Okay. This angle is phi. Look at this angle is phi. This angle is known as angle of shear or shearing angle. Okay. Next. Now a numerical. If strain of a wire of length 2 meter is 0.1%, find its increase of length. Look. Now we know the longitudinal strain is equal to increase of length divided by original length. This equal to 0.1%. Okay. Now look at the L divided by 2 meter. So this is the 2 meter and this is the 0.1% means 1 by 100. So look at this is the 2. So look at this, L equals to 2 into 10 to the power minus 3 meter is the elongation or increase of length of the wire. Okay. Next. Now elastic limit, the balance force or load up to which an elastic substance exhibits the property of elasticity is called elastic limit. The elastic limit of steel is much greater than elastic limit of rubber. That is why steel is more elastic than a rubber. Okay. Elastic limit generally expressed in terms of stress. More elastic stress, more is the elastic limit. Less elastic stress, less is the elastic limit. Okay. Now a numerical based on elastic limit. The elastic limit of a typical rock is 3 into 10 to the power 8 Newton per meter square. Density of the rock is 3 into 10 to the power 3 kg per meter cube. G is taken as 10 meter per second square. we have to calculate maximum height of a mountain on the earth's surface. So look at this. Here stress is equal to 3 into 10 to the power 8. Now stress is equal to force by area of cross section. So this is the force divided by area of cross section. This equals to 3 into 10 to the power 8. Force, that means weight. Weight means this is the area of cross section into height. This is the volume. This volume is, if this volume is multiplied by d, then this is the mass. If this mass is multiplied by g, then this becomes weight of the rock. This divided by capital A, this is the 3 into 10 to the power 8. Okay. Now look at this. This and this cancel out. Okay. So look at this. This is the h into d. D is the 3 into 10 to the power 3 into 10 to the power 3. And this is the 10. So this is the 3 into 10 to the power 8. Look at this. Here 10 to the power 3 into 10. That is 10 to the power 4. So look at this. This cancel out. So this is the 10 to the power 4. 3 cancel out. Therefore h is equal to 10 to the power 4. That is 3. That is 10 into 10 to the power 3. Therefore height of the mountain is 10 into 10 to the power 3 meter. That is h is equal to 10 kilometer. Okay, understood? Next, now Hooke's law. Within elastic limit, stress by strain is equal to constant. So here stress divided by strain is equal to constant. This constant is called elastic modulus. There are three types of elastic modulus: Young modulus, bulk modulus, and modulus of rigidity. Okay. Now Young modulus. Within elastic limit, the ratio between longitudinal stress and longitudinal strain is called Young modulus. So look at this. Young modulus y is equal to longitudinal stress divided by longitudinal strain. Look at this. This is a wire. Its length is capital N. If a load F equals to mg, acting on it, keeping apparent fixed, elongation becomes small l. So what is the strain? Strain is the increase of length divided by original length. So look at this. This is the increase of length by original length. What is the stress? Stress is the balance force divided by area of cross section of this wire. Suppose area of cross section capital A. So stress is the F by A. So look at this. This is the F by A. Okay, understood? Therefore y is equal to, this is the FL divided by A small l. Now look at this. Here F equal to mg. So look at this. Here mg capital L divided by pi r square small l. Okay. Now the increase of length small l, this is the FL divided by AY. Now for a two wire having different y, the ratio of the increase of length L1 by L2, this is the F1 by F2 into L1 by L2, and look at this and are inversely proportional. So look at this is the A2 by A1 into Y2 by Y1. Okay, and A2 by A1 can be replaced by pi R2 square by pi R1 square. Okay, look at this. Now a numerical. Look at this. Two wire A and B. It has length L but B has length twice L. Its radius of cross section R. Its radius of cross section R by 2. They are stretched by same force F. Now we have to calculate the ratio of elongation A and B. Now look at this. We know The small l is equal to, this is the FL divided by pi r square y. Okay. Now look at this. This is the LA by LB. So look at this. This is the FA divided by FB. Look at this. This is the LA by LB. And this is the RB by RA. This is the whole square. Into, look at this. This is the YB by YA. Okay. Now FA by FP, this is the F by F. Okay. LA is the L, but this is the 2L. So this is the 1 by 2. Now look at this. RB is the R by 2. And R is the R. So look at this. This is the half whole square. And look at this. Y same. So this is the 1. This cancel out, so this equals to 1 by 8. Okay. So elongation of A by elongation of B, this equal to 1 by 8. Okay, understood? Next, look at this. When the length of a wire is L1, when tension in it is T1, length L2, then tension T2, we have to calculate the natural length. Now look at this. When tension T1, the increase of length delta L, this equal to L1 minus L. When tension T2, what will be the increase of length? Look at this. This becomes L2 minus L. Okay. Now, as elongation is directly, look at this. As elongation is directly proportional to increase of length. So look at this. T1 by T2, this equals to this divided by this. That is, this is the L1 minus L divided by L2 minus L. Okay. Now multiplying this. So look at this. This is the L1 into T2 minus T2 into L. This equals to T1 into L2 minus T1 into L. Okay. Now look at this. This is the L1 T2 minus T1 L2. This equals to L into, this is the T2 minus T1. Okay. Understood? Therefore, L equals to natural length. This is the L1 T2 minus T1 L2. This divided by T2 minus T1. Okay. Understood? Next. Now a numerical relating to stress, strain and increase of length. Look at this. This is a rod of radius of cross section 2 cm, length 2 meter and y equals to 2 into 10 to the power 11 Newton per meter square. A load of 100 kg put on it. We have to calculate stress, strain and elongation, that is increase of length. Now look at this. Here force acting on the rod F is equal to, this is the 100 kg. So this is the 100 into 9.8 Newton. Okay. Now radius of cross section is 2 cm. Therefore area of cross section pi into, now centimeter should be converted into meter in SI system. Therefore this is the 2 by 100 square. So look at this. This is the 4 pi into 10 to the power minus 4 meter square. Now look at this. This is the 1.256 into 10 to the power minus 3 meter square. Okay. Understood? Now stress. What is the stress? F by A is the stress. Okay. Therefore, this is the 9.8 into 100 whole divided by 1.256 into 10 to the power minus 3. So look at this. This is the 9.8 divided by 1.256 into 10 to the power 5. This is the Newton per meter square. Okay. Understood? So look at this. S equal to, this is the 7.8 into 10 to the power 5 Newton per meter square. Okay. Understood? Now we have to calculate strain. Look at this, y is equal to, this is the FL by A small l. So look at this strain, small l by capital L, this is the F by A into 1 by Y. Okay, look at this, F by A, this is the 7.8, this is the 7.8 into 10 to the power 5. What is the Y? Look at this, Y is the 2 into 10 to the power 11. So look at this, this is the 2 into 10 to the power 11. Understood? So this becomes 3.9 into 10 to the power minus 6 is the strain. What will be the increase of length? If you put L equals to 2 meter, we can get elongation. So look at this, here small l by 2, this equals to 3.9 into 10 to the power minus 6. So look at this, small l equals to, this is the 7.8 into 10 to the power minus 6 meter is the elongation produced in this rod. Okay, understood? Next, now elongation of a rod due to its own length. Suppose area of cross section of this rod is A and length of it is L. So what will be the volume of the rod? Look at this, the volume of the rod is L into A. If rho be the density of the material of the rod, so what will be its mass? L A rho. Now weight of the rod, this is the LA, this is the volume into rho, mass into G, this is the weight of the rod. Now this weight acting at the center of gravity of the rod. Now center of gravity from the top point is L by 2. Now from definition of Y, this is the force means this is the weight, L A rho G. Now length, this is the top to center of gravity, so this is the L by 2 divided by area of cross section into increase of length. So look at this, L is equal to, this is the L square rho G, this cancel out, divided by 2y is the expression of increase of length due to its own weight. Okay, now a numerical. Look at this, a iron bar of length 10 meter hangs vertically. Find increase of length due to its own weight. Y given and density of the material is also given. Now elongation due to own weight L equals to, this is the rho G L square divided by 2y. Here rho is the 7800, so this is the 7800. G is taken as 10, L is the 10 square, and this is the 2 into 10 to the power 11 Newton per meter square. So look at this, this is the 7.8 into 10 to the power, this is the 6, okay, divided by 2 into 10 to the power 11. So this is the 3.9 into 10 to the power minus 5 meter is the increase of length of the wire. Okay, now look at this, a numerical. A rubber cord of length 8 meter, density of the material 1500 kg per meter cube, and y equal to 5 into 10 to the power 6 Newton per meter square. We have to calculate the increment of length due to its own weight, that is rho G L square by 2y. Look at this, here rho given, G is taken as 10 meter per second square, L given and Y also given. So look at this, the increment of length L equals to, this is the rho G L square divided by 2y. Rho is the 1500, G is the 10, L is the 8 square, and this is the 2 into 5 into 10 to the power 6. Okay, now look at this, this is the, now this is the 15. Now look at this, this is the 1.5 into 10 to the power 4 into, this is the 64 divided by 10 to the power 7. So look at this, 64 into 1.5, so this is the 96 into 10 to the power 4 divided by 10 to the power 7. So this is the 96 into 10 to the power minus 3 meter is the increment of length of the wire. Okay, next. Now vertical depression. Look at this. This is a wire AB of length 12. If a load mg is acting at the midpoint is lowered by something. The midpoint is lowered by an amount x. Now we have to calculate the expression of x. Okay, the increase of length of each section, this section or this section, this is the BD minus BC. So increase of length is equal to BD minus BC. Okay, now x is very small than the length of the wire. Okay, therefore small l is equal to, look at this, this is the BD is the root under of L square plus x square. This is the L square plus x square minus L. Now L square into 1 plus x square by L square whole to the power half minus L. Okay, understood? Look at this. This is the L into 1 plus x square by L square minus L. Look at to the power half. As x by L is very small, so x square by L square is also small. Therefore, this is the L into 1 plus x square divided by 2L square minus L. So this is the L plus this is the x square by 2L minus L. Cancel out. So this is the x square divided by 2L. Okay, this is the elongation. Now we have to calculate the force along the length of the wire. Suppose this is the tension T and this is the tension T. Okay, if this angle theta, this angle also theta, this angle also theta. Now resolve T along horizontal direction. This is the T cos theta. For this T, this also T cos theta. And vertical component of this T and this T both are T sin theta. So this is the 2T sin theta is the vertical force. Okay. Now T cos theta and T cos theta cancel out. So vertical force 2T sin theta is equal to mg. So look at this. This is the 2T sin theta. This equal to mg. Now look at this. 2T sin theta is the perpendicular by hypotenuse. So look at this. This is the x divided by BD into mg. Therefore, look at this. BD and BC almost equal. So look at this. 2D into x by BC equal to mg. Therefore, T equals to, this is the mg into BC divided by 2x. So this is the mgl divided by 2x. Okay. Now from definition of Young modulus, y is equal to, this is the force into length divided by area of cross section into small l. Now what is the tension? Look at this. Tension is the mgl by 2x and this is the L. Here what is the elongation? Look at this. Elongation is the x square by 2L. So this is the x square by 2L. So this is the mg divided by a into L by x whole cube. Okay. From this relation we can get x equal to L into, this is the mg divided by ay whole to the power 1/3. Okay. Therefore, depression x directly proportional to length. Greater the length, greater be the depression. A wire of length 1 meter is clamped horizontally such that the tension in the wire is 0. Its area of cross section 4 mm square, that is 4 into 10 to the power minus 6 meter square. Okay, now a load mg is placed at the midpoint. Here mg is equal to, look at this. this is the 2.16 into 10 Newton. If a load mg is placed here, now the midpoint is depressed like this. So we have to calculate this vertical depression. Okay. Now the formula of vertical depression x equals to L into, this is the mg by y into a to the power 1/3. Now L is the, look at this, this is the 2L. So L becomes half of its length. Okay. So look at this, this is the half m. Now mg is the 21.6, y is the 2 into 10 to the power 11, and this is the 4 into 10 to the power minus 6 whole to the power 1/3. Look at this, this is the half into, this is the 21.6 and this is the 4 and 2, so 8 into 10 to the power 5. Okay. Now 10 to the power 5 should be converted into 10 to the power 6 because its power is 1/3. Therefore look at this, this is the half into 216 by into 10 to the power 6. Okay. So look at this, so this is the half into 6 by 2 into 10 square. Therefore vertical depression, this is the 1.5 into 10 to the power minus 2 meter. Okay. Therefore vertical depression is 1.5 centimeter. Okay. Next, look at this, a steel wire of length 1 meter is connected horizontally between two supports. If a load of 100 gram, that is mg equal to 0.1 into 10, that is 1 Newton, applied at the midpoint, we have to calculate the depression. Look at this, the wire becomes this. We have to calculate this depression x. Now depression x equals to half length into mg by ya to the power 1/3. Okay. So look at this, here m given, y of steel is known, area of cross section a is given. We have to calculate x. Now x equals to, this is the L, 12 is the 1 meter, so L is the half meter. Okay. Now mg means, look at this, this is the 1 Newton, and y is the 2 into 10 to the power 11, and a is the 0.5 into 10 to the power minus 6 to the power 1/3. Okay. Now look at this, this is the half into, this is the 1 by 10 to the power 5. Okay. So to the power 1/3. So look at this, this is the half into 10 by, this is the 10 to the power 6 to the power 1/3. Okay. Now look at this, this is the half into 10 to the power 2 into 10 to the power 1/3. Okay. Now 10 to the power 1/3 means 2.13 divided by 2 into 10 to the power 2 is the unit is meter. So look at this, this is almost 1 into 10 to the power minus 2 meter, that is 1 centimeter is the depression of the midpoint. Okay. Understood? Next. Now bulk modulus. Within elastic limit, bulk modulus is the ratio between volume stress and volume strain. Look at this, this is the volume stress divided by volume strain. Okay, look at this, this is a sphere, a normal force acting on this sphere, so its volume decreases from capital V to V minus small v, where small v be the decrease of volume. Then volume strain becomes small v divided by capital V. If F is the normal force, look at this. So volume stress K equal to normal force by area is the normal stress divided by, this is the small v by capital V. Now normal force by area is the pressure. Therefore, the bulk modulus K equal to pressure divided by volume strain. This can be written as P capital V by small v. Okay? The reciprocal of bulk modulus is known as compressibility. So, compressibility equal to 1 by bulk modulus. Okay? Now, change of volume by original volume can be written as change of density divided by original density. So, look at this. K can be represented as K equal to P divided by, this is the delta rho by rho. Therefore, delta rho by rho, this equal to P by K is another relation with variation of density with pressure and bulk modulus. Okay? Now some numericals relating to bulk modulus K. Now we have to calculate the increase of pressure to change the volume 0.01%. Bulk modulus is equal to 2.1 into 10 to the power 9 Newton per meter square. So look at this, we know K is equal to, this is the P, change of volume by original volume. So P equal to, this is the K into small v by capital V. Now K is the 2.1 into 10 to the power 9 and small v by capital V is the 0.01%. Now this into 0.01 and percent means 1 by 100. So look at this, this is the 2.1 into 10 to the power, this is the 1 by 100, 1 by 100, so this is the 10 to the power 5 Newton per meter square is the increase of pressure to change the volume 0.01%. Okay? Now a numerical. The density of seawater is 1030 kg per meter cube. We have to calculate the change of density of seawater at a depth of 400 meter. K is given 2 into 10 to the power 9 Newton per meter square. The formula of K with the variation of density of water, K equal to increase of pressure divided by delta rho by rho. So from this equation we can write delta rho by rho, this is the P by K. Therefore delta rho equal to P into rho divided by K. Now P is the pressure of 400 meter water column. So look at this, this is the 400 into 1030 into 10 into 1030 divided by, this is the 2 into 10 to the power 9. Look at this, this is the now look at this, here 20, here 0, here. Now look at this, the numerator can be written as 4 into 1.03 into 1.03 into 10 to the power, look at this, this is the 2, 3, 1, 3, 6, 7 and 9, 10 to the power 9 divided by 2 into 10 to the power 9. This and this cancel out. So this is the 2 into 1.03 whole square. So 2.2 kg per meter cube is the increase of density of seawater at the depth of 400 meter. Okay? Understood? Next. Now modulus of rigidity. Within elastic limit, modulus of rigidity N is defined as the ratio between shearing stress and shearing strain. Suppose this is a cuboid. Here height of this cuboid is L. A tangential force acting at the top end where lower end is fixed. A tangential force is F acting at the upper. Now a tangential force acting at the upper surface while lower surface is fixed. So upper surface is displaced by a very small amount. Suppose this is the x. So look at this angle phi. So from here we can write phi equal to, this is the x by L. So here shearing stress becomes applied force by area of cross section, and strain becomes, this is the x by L. So look at this, F divided by A phi is the bulk modulus. Okay, understood? Now a numerical of N. A steel plate of area 4 centimeter square and edge is 0.5 centimeter. A tangential force acting on the upper surface. Look at this. This is the upper surface. Now we have to calculate displacement of upper surface with respect to the lower surface. This is the x. Now from definition of N, we know N equal to, this is the shearing stress divided by shearing strain. Okay, so look at this shearing strain, this is the F by A into N. Here x equals to, this is the F into L by A into N. Okay, this is the displacement of upper surface with respect to the lower surface. Okay, look at this, F is the 10 Newton, L, this is the 0.5 centimeter, it should be converted into meter. So this is the 10 to the power minus 2, okay, and A is the 4 centimeter square, so 4 into 10 to the power minus 4 meter square. N is the 8.4 into 10 to the power 10 to the power 10. Okay, now look at this, this is the 10 to the power 6. Look at this, and this means 10 to the power 6, and look at this, so this become 5 by 4 into 8.4 into 10 to the power minus 8 meter is the displacement of top surface with respect to the bottom. Okay, this equal to 0.15 into 10 to the power minus 8 meter is the displacement of the top surface with respect to the bottom. Okay, understood? Next, now Poisson ratio. When a wire is stretched, its length increases. Simultaneously, its diameter also decreases. Look at this. This wire has initial length capital L and initial diameter capital D. If a balance force acting on it, its length is increased by small l. Simultaneously, diameter is decreased by small d. Therefore, longitudinal strain and lateral strain also occur simultaneously. The ratio between lateral strain, that is small d by capital D, and longitudinal strain small l by capital L is constant. This constant is called Poisson ratio. So Poisson ratio sigma equal to lateral strain divided by longitudinal strain. Okay, now what is the lateral strain? Lateral strain is the change of diameter divided by original diameter. So look at this, this is the small d by capital D, and longitudinal strain, look at this, change of length by original length. So this is the small l by L. Therefore, sigma is equal to small d capital L by small l capital D is the expression of Poisson ratio. It is not an elastic modulus because it is the ratio between the two strain, but elastic modulus is the ratio between stress and strain. That is why it is not the elastic modulus. It never be negative because negative value of sigma means length and diameter increases simultaneously, but there is no material present in our nature. Okay, the theoretical value of sigma lies between -1 to 0.5. but its practical value lies between 0.2 to 0.3. Okay, now we have to express the relation between volume strain and longitudinal strain in terms of sigma. Suppose initial volume of a wire is V equal to pi d square by 4 into L. Now we have to express the relation between delta V by V and delta L by L, that is volume strain and longitudinal strain in terms of sigma. Look at this, taking log from here. So we get this is the log V equal to log pi by 4 plus 2 log D plus log L. Okay, understood? Now differentiating this expression. Look at this. This is the dV by V. This is 0 plus 2 dd by D plus 2 plus dl by L. Okay. Now dV by V is the volume strain. Look at this. Now this is the dl by L. This is the 1 plus 2 d by d divided by dl by L. Okay. Now this becomes dV by V equal to dl by L equal to 1 minus, look at this, 2 into, this is the minus dd by d divided by dl by L. Okay. Now minus dd, that means decrease of diameter. So look at this, the decrease of diameter by original diameter divided by increase of length by original length. This is the sigma. Therefore dV by V equal to dl by L 1 minus 2 sigma. This is the expression of longitudinal strain and volume strain in terms of Poisson ratio. Okay, understood? Next, look at this. A load of 10 kg weight is suspended in a wire of length 1 meter. The increase of length of it is 0.1 centimeter, that is 0.001 meter. Sigma equal to 1/3. If area of cross section is 0.1 centimeter square, we have to calculate the increase of volume. Now look at this. We know dV by V, this equal to dl by L into 1 minus 2 sigma. Look at this. Here L is given, dl is given. So look at this. This is the 0.001 divided by, this is the 1 into 1 minus 2 into 1/3. Okay, this is the 0.001 into 1/3. Now this is the dV and V equals to area of cross section into length. So look at this, dV is the 0.001 into 1/3 into A. Look at this. This is the 0.1 centimeter square. So this is the 0.1 into 10 to the power minus 4 meter square. Okay. And L is the 1 meter. Okay. So here look at this. This is the, look at this. This is the 1/3 into, this is the 10 to the power minus 3. This is the 10 to the power minus 1. So 10 to the power minus 8 meter cube. That is 0.33 into 10 to the power minus 8 meter cube is the change of volume of the wire. Okay. Next. Now elastic potential energy. When a balanced force acting on an elastic substance, a reaction force is produced in it. The work done against this reaction force is stored as a potential energy in the substance. This potential energy is called elastic potential energy. Now we have to express the expression of elastic potential energy. Look at this. If small l be the increment of length due to balance force F, then from definition of Young modulus we can write F by A divided by small l by L. Okay, now from this relation F equal to y A into small l divided by capital L. Therefore F directly proportional to increase of length. Therefore the reaction force is not constant, it is a variable force and it directly proportional to increment of length. Therefore the potential energy or work done against the reaction force W equal to U equal to, this is the average force by 2 into elongation, because when force 0, elongation 0, when force F, elongation small l. So look at this is the half into F into L. This is the expression for potential energy. Now this energy can be expressed in terms of Young modulus. If we replace F by this formula, so you can get half, this is the y A small l square divided by L. Therefore potential energy U directly proportional to L square, that is U directly proportional to square. Therefore potential energy U directly proportional to L square, that is square of the increment of length. If 1 joule be the potential energy for increment of length of 1 millimeter, then the potential energy for increment of length 2 millimeter is this is the 2 square, that is this is the 4 joule. Now increment of 3 millimeter, the potential energy, this is the 9 joule. Okay, understood? Now we have to express the energy density in elastic substance. Now look at this, the energy density, that is energy by volume, this is the half F into L divided by, look at this is the half F into L, and this is the volume, that is A into L. A means area of cross section into length. Now look at this is the stress, this is the strain. So energy density U by V, this equals to half stress into strain. Now strain can be replaced by, look at this is the stress by strain. So strain can be replaced by Y by Y. So look at this is the half into S by Y. So look at this, the energy density can be also expressed as S square by 2Y, that is stress square divided by 2 into Young modulus. Okay, now energy stored in spring. Look at this is a spring. If a balance force F acting on the spring, its increment of length F proportionate x. Therefore F equal to Kx, where K is force constant, which is equal to, look at this is the F by x. If x equals to 1, then K equal to F. Therefore force constant is the force required for unit elongation of the spring. Its unit is Newton per meter and dimension mt minus 2. Look at this, dimension is the mlt minus 2 divided by L, so this is the mt minus 2. Okay, now if the spring is cut into 2 equal parts, look at this, if the spring is cut into 2 equal parts, then increment of length due to force F is obviously x by 2. So force constant of this half part k dash, this is the force F divided by x by 2. So look at this, this is the 2 into F by x. So this is the 2k. Therefore force constant is twice the initial. In the same way, if the spring is cut into 3 equal parts, force constant of each part, this is the 3k. If the spring is cut in the ratio m is to n, then force constant of first part k1 is the m plus n divided by m into k, and force constant of second part, this is the m plus n by n into k. Okay, so larger the length, smaller the force constant. Okay, now energy stored in the spring. We know that energy stored is the half into F into increase of length. Now F equal to kx. So this is the half k x into x. So this is the half k x square. Now energy can be expressed in terms of force applied. If we replace x equal to F by k, we can get, look at this, u equal to half k, this is the F by k whole square. So look at this, this is the F square by 2k. This is the another expression for energy stored in the spring. Okay, now a numerical related to these two expressions. Okay, look at these two springs having force constant k1 and k2 are stretched by same length and same force. Which spring stores more energy? Now numerical 1. Suppose increment of length in each spring be x. So energy stored in first, this is the half k1 x square. Energy stored in second, this is the half k2 x square. So u1 by u2, this is the k1 by k2. Look at this by this equal to this by this greater than 1. Therefore u1 greater than u2. Okay, understood? Next, look at it. If they are stretched by same force, suppose applied force F. So u1 is the, this is the F square by 2k1. And u2 is the F square divided by 2k2. Now if we divide this by this, we can get u1 by u2. This is the k2 by k1. So this is less than 1. Therefore u1 less than u2. So when they are stretched by same length, the energy stored in first greater than energy stored in second. When they are stretched by same force, the energy stored in second greater than energy stored in first. Okay, understood? Now next, look at this. This is a spring of length L, force constant K. Increase of length is x. Find amount of work done the further increment of length y. That is initial elongation x and final elongation x plus y. We have to calculate the energy stored to increment of length y from x. Okay, now look at this. Initial energy stored u equal to, this is the half k x square. Final energy stored, this is the half k, this is the x plus y whole square. Therefore work done, this is the u2 minus u1. Okay, now look at this, this is the half k. Look at this is the x plus y whole square minus x square. Okay, a square minus b square, a plus b into a minus b. So look at this is the half k, this is the x plus y minus x into x plus y plus x. Okay, this and this cancel out. So this is the half k y into 2x plus y. Okay, understood? Next, if a load is applied on an elastic substance, its strain occurs. Simultaneously, a reaction force produced in it. Therefore, stress is also produced. Now, if we draw the stress-strain curve of an elastic substance, look at this. This graph is the straight line from O to A. Here, stress proportional strain. This OA region is called proportional limit. If we apply the load further, we reach a point B in which the proportional limit is not obeyed. But if load is removed, the body regains its initial state. This is known as elastic limit or yield point. Okay? If we increase the further load, we reach a point C where permanent elongation, this amount OC dash is occurred. Okay? After C, the body gains the plastic property. So further increment of length, the elongation is more in comparison to the application of force. Finally, we reach a point D where the substance breaks. This point is known as fracture point. Okay? Understood? Many thanks for watching this video. This video will be extremely helpful for class 11, NET, main and advanced. If you are benefited from this, please subscribe my channel to learn physics easily. Okay?